We will be looking at basic proportionality theorem. Don't worry, we will make it easy for you. What you see on your screen is triangle ABC. You also see a line L which is highlighted in purple color. This line L is parallel to BC, and this line L intersects side AB at point P and intersects side AC at point Q. What does basic proportionality theorem says? It says if a line parallel to a side of a triangle intersects the remaining sides in two distinct points, then the line divides the side in the same proportion. Here we have the same case. We have line L parallel to one side of a triangle BC. This theorem, it says the line will divide the remaining two sides in the same proportion. The remaining two sides are AB and AC. So what it means in simple term? It means the ratio of AP upon PB is equal to AQ upon QC. Now why this is possible? Because line L is parallel to BC, that means one side of a triangle. Let me show you one case now. Do you see one more line which is highlighted in red color? This line is intersecting side AB and AC at point R and point T. But the ratio of AR upon RB is not equal to ratio of AT upon TC. Why? Because RT is not parallel to BC, or to that case RT is not parallel to any side of that triangle. Hence, it is not dividing the remaining two sides in equal proportion. But in the case of line L or PQ, the ratio of AP upon PB is equal to AQ upon QC. Why? Because PQ is parallel to BC. Did you get this? Let's prove basic proportionality theorem. So in triangle ABC, we have been given that line L, which is highlighted in purple, is parallel to BC. This line intersects AB at point P and AC at point Q. So let's prove AP upon PB is equal to AQ upon QC. To do this, let's connect point B with point Q with a straight line. What it does is, it creates two distinct triangles, triangle APQ and triangle PQB. For ease of understanding, I have taken out these triangles separately. Now, in triangle APQ, which is highlighted in blue, let's assume AP as the base. And triangle PQB, which is highlighted in green, let's assume PB as the base. If we assume this, then QT is the height for both the triangles. Why? Because QT is perpendicular to the base AP as well as base BP. Hence, QT is the height for both the triangles. And we have already seen, when the height is same, then the ratio of areas of triangles is equal to their ratio of their bases. Hence, area of triangle APQ upon area of triangle PQB is equal to AP upon PB, as AP is base for triangle APQ and PB is base for triangle PQB. Now if you pay attention, AP upon PB was our LHS. So we have got our LHS. I am keeping the derived LHS over here and calling it as 1. And now I have connected point P to point C. What it has done is, it has created again two distinct triangles. Triangle APQ highlighted in blue, triangle PQC highlighted in yellow. And again, for ease of understanding, I have taken out these two triangles separately over here. In triangle APQ, which is highlighted in blue, let's assume AQ as the base, and in triangle PQC, which is highlighted in yellow, let's assume QC is the base. In that case, PR would be the height for both the triangles, as PR is perpendicular to both AQ and QC. As the height is same, area of triangle APQ upon area of triangle PQC is equal to AQ upon QC. AQ is the base for APQ and QC is the base for PQC. If you pay attention, AQ upon QC is our RHS. But wait, we have got our LHS, we have got our RHS, but we haven't proved LHS is equal to RHS. We will be doing that. Now I want you to pay attention to highlighted triangles, triangle PQB highlighted in green and triangle PQC highlighted in yellow. In triangle PQB and PQC, PQ is common. Let's assume that as a base for both the triangles. In that case, BM and CN would become height for both the triangles, as BM is perpendicular to PQ, CN is perpendicular to PQ. But BM and CM are equal. Why? Because BC is perpendicular to MN. So we can conclude area of triangle PQB highlighted in green is equal to area of triangle PQC highlighted in yellow. Why? Because area of triangle is equal to 1/2 base into height. In this case, base is also common or same and height are also similar. So areas also would be similar. Hence we have derived area of triangle PQB is equal to area of triangle PQC. Let's call it equation 3. Now if we take a look at equation 1 and 2, we find numerator is same, which is nothing but area of triangle APQ. And in the third equation, we have proved area of triangle PQB is equal to area of triangle PQC. But area of triangle PQB is denominator for equation 1 and area of triangle PQC is denominator for equation number 2. That means both numerator and denominators are same for equation 1 and 2. Hence we can say area of triangle APQ upon area of triangle PQB is equal to area of triangle APQ upon area of triangle PQC. That means our equation number 1 and 2 are equal. If equation 1 or 2 are equal, that means AP upon PB is equal to AQ upon QC. Hence, proved. Let's now look at the converse of basic proportionality theorem. What it says is, if a line divides two sides of a triangle in the same ratio, then the line is parallel to the third side. In triangle ABC, line L is such that it is dividing AB and AC into equal proportion. That means AD upon DB is equal to AE upon EC. In this case, line L would be parallel to BC, that is third side of a triangle. In simple word again, if AD upon DB is equal to AE upon EC, then line L or DE is parallel to BC. This is converse of basic proportionality theorem. Let's prove converse of basic proportionality theorem. To do this, we have given data as AD upon DB is equal to AE upon EC, and we need to prove DE is parallel to BC. Let's prove converse of basic proportionality theorem. To do that, we have given data as AD upon DB is equal to AE upon EC. With this data, we need to prove DE, that means line L, is parallel to BC. For a moment, let's say DE is not parallel to BC. If DE is not parallel to BC, there would be some line which is parallel to BC. So let's draw DE dash and say it is parallel to BC. Now if DE dash is parallel to BC, then AD upon DB is equal to AE dash, upon E dash C based on basic proportionality theorem. But based on a given data, we know AD upon DB is equal to AE upon EC. Now for these two equations, left hand sides are same, which means the right hand sides are same also. Hence, AE dash upon E dash C is equal to AE upon EC. These two are nothing but right hand sides of both these equations. So AE dash upon E dash C is equal to AE upon EC. Let's call this 1. Let's write down derive equation here and add 1 to both the side. 1 here I mean number 1 adding to both LHS and RHS, we get AE dash upon E dash C plus 1 is equal to AE upon EC plus 1. For addition, we make the denominator common. Hence, we get AE dash plus E dash C upon E dash C is equal to AE plus EC upon EC. But if you look closely, AE dash plus E dash C is nothing but AC. Hence, we can say AC upon E dash C. But at the same time, AE plus EC is also equal to AC. Hence, we can also say AC upon EC here. In the given ratio, if numerators are same, that means denominators are also same. Hence, we can conclude E dash C is equal to EC, which means E dash and E are the same points. And what we have assumed? We have assumed DE dash is parallel to BC, but E dash and E are the same point. Hence, we can say DE is parallel to BC.